Hello everyone. Today we are going to study common emitter amplifier. In earlier videos we have seen common base, common emitter configurations, but in this video we are going to study the operation construction of common emitter amplifier. So let us start. Before going to the operation of common emitter amplifier, we'll see what the amplification is. Amplification is a process which increases the signal strength by increasing the amplitude of a given signal without changing its basic main characteristics. In amplification, the input signal may be a current signal, voltage signal, or a power signal. Amplifier amplifies the signal without changing its characteristics. Amplifiers can be used in communications, audio, video instrumentations, and they can be used in controllers. Since we are studying common emitter amplifier, in which we are going to use transistor, and this transistor common emitter configuration mode transistor, this mode can be used as an amplifier. This transistor can work as amplifier only when the transistor works in active region, which lies between saturation and cutoff region. So let us see how the operation of this CE amplifier is done. Here, when a signal is applied across the base emitter junction, the forward bias across this junction increases during the upper half cycle. This leads to an increase in flow of current from the emitter to the collector through the base, and hence this collector current increases. The increasing collector current makes more voltage drop across the collector load resistor, that is this RC. The negative half cycle, for the negative half cycle, this negative half cycle decreases the forward bias voltage across the emitter base junction. The decreasing collector base voltage decreases the collector current in the whole collector resistor RC. Thus, the amplified load resistor appears across the collector resistor. So this is all about the operation for first half and second half cycle. Okay, now let us see the construction of this CE amplifier and its working also. This common emitter amplifier circuit is consisting of a transistor and a voltage divider biasing used to supply the base bias voltage as per the requirement. This voltage divider biasing has a potential divider with two resistors. They are connected in such a way that the midpoint is used for supplying the base bias voltage. There are different types of electronic common emitter amplifier, and here in this we are using R1 resistor used for forward bias and R2 for the development of bias. This load resistance RC and RE is the resistor for thermal stability. We had connected the C1 capacitor, which is used to separate AC signal from DC biasing voltage, and the capacitor is known as coupling capacitor. Here, if the resistor R2 increases, then there is an increase in the forward bias, and R1 and bias are inversely proportional to each other. The alternating current applied to the base of the transistor of the common emitter amplifier circuit, then there is a flow of small base current. Hence, there is a large amount of flow through the collector, which helps this RC resistance. The voltage near this RC will change because of the value is very high, and this value can vary from 4 to 10 kilo ohms. Hence, there is a large amount of current present in this collector circuit. This amplified from the weak signal, therefore, common emitter transistor works as an amplifier circuit. Now let us see the voltage gain in this common emitter amplifier. The current gain of the common emitter amplifier is defined as the ratio of change in collector current to the change in base current, and the voltage gain is defined as the product of current gain and the ratio of the output resistance of the collector to the input resistance of the base current. So here we can write this beta, that is the current gain, is equal to del IC upon del IB. Let us see another very important point, which is called DC load line, and Q point. Here we have a load line diagram for a resistive load in common emitter circuit. This load line shows how the collector load resistance, that is RC we had mentioned, makes the circuit voltage and current. This diagram plots IC versus VCE for different values of base current. For different values of base current. Here we can write IB. The intersection of this load line with the transistor characteristics curve represents the circuit concerned values of IC and VCE at different base current. If the transistor could pass all the current available with no voltage drop across it, the collector current would be the supply voltage VCC over it. This is the point where the load line crosses the vertical axis even at saturation point. This is the saturation point A. Even at saturation, there will be some voltage from collector to emitter. When the load line crosses the horizontal across the transistor, current is minimum, the transistor is said to be of cutoff and passing only very small leakage current, and the entire supply voltage appears as VCE. The load line is the line of DC equivalent circuit defined by reducing the reactive components to zero, and it is used to determine the correct DC operating point, and this point is called Q point. Now let us see some of the important points which are terminologies which just now we gone through, and these points are cutoff region, active region and saturation region. So what actually this cutoff region is? We have just now seen a point B and it is called as cutoff region on the load line graph. So in the cutoff region, this transistor will be get off, and in saturation region, transistor will get on. These regions are mainly used in switching conditions. And in the active region, transistor will be on. The collector to emitter voltage will be in between cutoff and saturation region. Just now we have seen the point A and point B. Point A is saturation region and point B is the cutoff region. Transistor can amplify the small changes in voltage at base which is given to the collector. Transistor requires only 0.7 volt to work completely in saturation mode. Whereas saturation region is the, we just now we observed point A. And in the active region, collector current IC is proportional to the base current by a constant multiplier called beta, and IC is equal to beta times IB. By this, we can easily use transistor as a linear amplifier in active region. With this, I stop here. Thank you.